situations in which friction is not involved. Now we got to start tackling the idea of friction. So we're going to start simple and work our way up. The simple aspect is dealing with flat surfaces. The flat surface friction, all we're going to do is we're going to push a crate forward with no angle of attempt. It's just going to be straight across 0-degree push. And then we're going to look at the two aspects of what friction is based upon. Now, the definition of friction is basically a resistance to motion. It's working in the exact opposite direction of the motion. So, if you push on an object and it's not moving, it's because the force of friction is greater than your push. Once you get to that point where it starts to move, you've now overcome what we call static friction. The word static means not moving. Like static electricity is a bunch of electrons building up your body. When you, in the wintertime, you're scraping your feet against a rug or a tile floor or anything, then you stick your finger up to somebody's nose, then the electrons jump at that point. It's static before that, and then it's kinetic after that. Okay? So that's the same thing for friction. It's opposing your force, and if you don't have enough force to push, it's going to stay there. But once you get to that exact moment where the two are equal, then it starts to move. Just like a hair past that point. So we say for all practical purposes, that force is the same as the force pushing back when it starts to move, because you're reaching that threshold. So it's actually like a very, very infinitesimal more for those in calculus. That point where it's infinitesimally greater than the friction pushing back on you, that's what we're going to consider as the force of friction. And we're going to use F sub F for the force of friction. Now, at the same time, the reason why there is resistance is because the two surfaces are working against each other. Now, if you take a look at it from what we call a macro sense, or a large scale view of it, you don't see much difference between the two, but there is a lot of contact between the two. You take a microscopic look at it, you see the surfaces are not as smooth as they appear to be from a macro sense. So we got those interactions going as well. But the point is, they have to overcome that pressing against each other in order to move. Okay? And so the normal force of pushing down on the surface is the second factor that you have to look at. We call it F sub N. So you got F sub F for the friction. That's the horizontal aspect of it that you're trying to push it. And then you also have the perpendicular version, or I want to call it the vertical version of it, which is Fn. Now for flat surfaces, the normal force, the perpendicular force, is going to be the weight. And the horizontal force, the F sub H is what we would call it at this point, is the opposite of the applied force. And what we're just going to look at, instead of from the applied force, we're going to look at it from the frictional point, which is exactly and equally opposite to each other. Okay? So we have a symbol to represent that, and we call that symbol the coefficient of friction. Alright, so the coefficient of friction is symbolized by the letter mu. Now remember, the mu is like a little kitty cat walking to the right, it's got a tail going behind it, and it's going mew, 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 mew. See, that's how you're remember that. Okay, moving on. So, there's two types of friction. Static friction, which is what we're talking about, getting the thing to move. And then once it starts to move, we call that kinetic energy. Because the word kinesis is the Greek word meaning motion. Kinetic energy is the energy of motion. You've heard the word kinetic before. That's where it comes from. It's a Greek word. Static means still, and kinetic means moving. Static friction, which we symbolize, if we want to differentiate it, as mu sub s, is the amount of force needed to get an object moving. We talked about that. And the kinetic friction, mu sub k, is the amount of force to keep it moving. Once you got it moving, it's going to keep moving, and so you apply a different amount of pressure. You have to overcome the static in order to get it moving. Therefore, the static friction value is always going to be higher than the kinetic friction value. Now, these are decimal values, but they can be greater than 1. Most of them are not. Most of them tend to fall less than 1. But in really sticky situations, like if you have like a carpet can be really difficult to push objects across, especially if it's got like all kinds of 70s looking characteristics. Instead of a smooth carpet, you got all this fluffy stuff all around, because that was the thing in the 70s. And so that's going to have I'll probably have a kinetic factor greater than 1. So, to use that, let's talk about this example. What is the coefficient of static friction for a 40 kilogram crate that requires 80 newtons of force to get it to move? So we're looking at static mu sub S. So let's draw this scenario right here. Here's your floor, and then on the floor, you're going to have some kind of crate. And you said that's 40 kilogram crate. And you're going to push it forward just to get it to move at 80 newtons. And the question is, what is the mu value? We can put mu sub S, but we understand. Mu is mu, as any cat knows. So, this is defined as F of F over S of N. And so the force of friction is equal to the force to get it to move. So while this is actually the applied force, the frictional force is going in the opposite direction, but equal to it. Okay? So this is, while we're looking at this, and this is actually what the value is, this is actually what we're entertaining as the frictional force. So we put 80 newtons on top. Now the normal force here is the gravitational attraction, because this is not on an inclined plane, it's just sitting there flat. So that means then that the F of N is equal to the F of W. Again, I keep using that capital N because that's a habit I got into. Rewrite that. F sub N equals F sub W. Because I don't want people thinking that somehow that's involving newtons at that point. We'll put the newtons down here as capital N. So we can find F sub N as M times G. So that's going to be 40 kilograms times 9.80 meters per second squared. And that's going to equal 392 newtons, capital N. So I'll put that 392 newtons right there. And so mu is just going to be the decimal value of this fraction. So you calculate, take 80 divided by 392, and you notice then that the newtons will indeed cancel out. There will be no label for mu. And the answer we got for that is 0.204. And again, no label for mu. It is just a ratio, simply saying that it takes an effort in relationship to the forward push versus the downward push of 0.204. The smaller the number, the less the less frictional force you have to overcome. The larger the value, particularly when you get up to like 0.7, 0.8, 0.9 and above the ones, it's going to be really hard to push it. So you have to find some other way to move it without manual pushing or pulling, which is something we'll take up pretty soon. So, practice problems. I want you to find the coefficient of friction for these three scenarios. And good luck.